Hey guys, this looks like a fun one. We're given a circle that contains a square and two overlapping equilateral triangles. And it wants to know what is the area of this overlap. This is day 19 of the 2025 Advent calendar. And if you want to try this one, pause it right now because I'm going to solve it in 3, 2, 1. Since we were given that these are equilateral triangles, we know that these three angles will be 60 degrees and these three angles will be 60 degrees. And now for the next step, I think I have to make an assumption. I'm assuming this side is parallel to this side. I know for sure this is parallel to this, but I don't know if we know for sure these are parallel. So I'm going to make the assumption that every line that looks horizontal is horizontal. Given that assumption, these two angles would also be 60 degrees. And that's because they're corresponding angles with this transversal and these two parallel lines. And then we would also know these are 60 degrees for the same reason. It'd be this transversal with these two parallel lines. And since we know this is an equilateral triangle, we can make a formula for the question mark. Let's use these notes for equilateral triangles. If the side length of this equilateral triangle is equal to s, then we can say the area is equal to root 3 over 4s squared. That's from this right here. Or if we know that the height is equal to h, we could also use this formula, which would be h squared over root 3. So all we got to do is find the side of this equilateral triangle or the height of the equilateral triangle. Then we can find the answer to the question. Let's put a box around this and move it down here. For the next step, since we know this is an equilateral triangle, we know all three of these sides are going to be congruent. And then the base of this equilateral triangle is shared with the side of this square. That means all of these sides will also be congruent with the sides of this triangle. And then this equilateral triangle also shares a side with the square. So these two sides of this triangle will also be congruent to all these other congruent sides. Let's clean things up a little bit and let's connect this point to this point. And we can focus on this triangle right here. It's going to be an isosceles triangle since two of the sides are congruent. That means these two base angles are going to be congruent to each other. And then for the last angle, we already know this is 60 and we know this is 90. So that means this whole angle will be 150 degrees. And then since this is 150 degrees and these two are congruent, each of them have to be 15 degrees because we need all three of the angles to add up to 180 degrees. And now from here, let's draw this side and this side to make another triangle. It's possible for us to show that this triangle is congruent to this triangle. First, this side is congruent to this side. We showed that earlier. Let's bring back the mark. And then this side is shared with the triangle, so let's mark that. And then for this angle right here, since this angle is 60, and we know this one's 15, and the whole thing is equal to 90, that leaves 15 for this one right here. Because 60 plus 15 plus 15 is equal to 90. Now by side angle side theorem, we know that these two triangles are congruent. Anytime you have two triangles that contain two pairs of congruent sides and the angle in between those sides are also congruent, you know the two triangles are congruent. And then since these two triangles are congruent, we also know that this side is congruent to this side. So we can give it a dash mark. That's called CPCTC. It stands for congruent parts of congruent triangles are congruent. Now we can bring back the circle and let's clean things up a little bit. Let's bring back this side of this triangle. And now we notice something special about this point right here. This point is equidistant from 3 points on the circle. That's only going to be possible if this is the center of the circle. So that means I could draw another segment from here to here, and that would also be a dash mark. And we can mark all these dash marks as R because they're all going to be the radius of the circle. And then any of these other lines with the dash mark, like this one right here, it would also be equal to R. All of these dash mark segments will be the same length as the radius of the circle. And now we have enough information to solve for the radius of this circle. This is an equilateral triangle where we know the area and we know the side length is equal to R. Let's use these notes right here. The area is equal to root 3 over 4R squared. And in the place of the area, we can plug in 24. So now we have one equation and one variable. Let's solve for that variable. First, we can get rid of this root 3 divided by 4 by multiplying both sides by the reciprocal. 4 divided by root 3. On the left-hand side, 4 times 24 is equal to 96. And then to rationalize the denominator, we can multiply top and bottom by root 3. On bottom, the root 3 times root 3 is equal to root 9, which is equal to 3. And 96 divided by 3 is equal to 32. So on the left-hand side, we have 32 square root of 3. And then on the right-hand side, this fraction and this fraction are going to cancel each other out. So we end up with r squared. And then from here, we can square root both sides. On the left-hand side, it's going to be the square root of the quantity 32 square root of 3. And then on the right-hand side, since r is a positive distance, the square root of r squared is going to equal r. Let's move the r to the left-hand side and we can clean this up a little bit. Let's scoot this over, and in the place of the 32, let's plug in 16 times 2. And now this and this can each get their own square roots. Square root of 16 is equal to 4, so r is equal to 4 square root of the quantity 2 square root of 3. So we know that the radius of this circle is equal to 4 square root of the quantity 2 square root of 3. And now let's go back to our original triangle. Let's draw this at right angles and complete this triangle. This side of this triangle is the same thing as the height of our question mark triangle. So we're going to end up using this equation to solve the area. So how are we going to solve for this height? Well, this angle is equal to 30 degrees. Anytime you have an equilateral triangle inscribed in a circle, the radius from the center to this vertex will always bisect this angle. And this angle will always be 60 degrees, so the bisected angle is 30 degrees. Here's some notes for that right here. And then since this is 30 and this is 90, that means the last angle is going to be 60 degrees. In every single 30, 60, 90 triangle, the hypotenuse is always double the length of the shortest side. And then since the hypotenuse is equal to 4 square root of the quantity 2 square root of 3, that means the shortest side is going to be half of that, which is 2 square root of the quantity 2 square root of 3. And now we're ready to solve for the area. In the place of this h, we can plug in all of this. The square will then go to each of these, giving us 2 squared and then all of this squared. 2 squared is equal to 4. The square root and the square are going to cancel each other out, and this root 3 on top and this root 3 on bottom are also going to cancel each other out. 4 times 2 is equal to 8, and let's give it a label of square units. This is the answer to our question. Let's put a box around it. In this given problem, and assuming that this is parallel to this, the area of this overlapping region is equal to 8 square units. How exciting. And this is the next question. We're given a semicircle where these arcs are congruent. And we're also given that this has a length of 3. And it wants to know what is the total shaded area, the area of these added together. This should be a fun one. How exciting.